Welcome to today's session of the Discrete Mass 2 course. I was just about thanking the people in the audience for making it worth my while to be here. Otherwise, I would just be doing distance education. Most of them are sitting at the back, so I'm still doing distance education, but it's not that far away. They are not in the United States or somewhere else. So what we're going to do in this part of today's course session is to wind up our discussion of vector geometry. As usual, we are going to get started by refreshing our memory of what we were doing last time around by solving a couple of exercises. After that, we'll move on to the new topics for this part of today's course session, which will be how to compute projection of vectors on lines and how to write equations for the planes, in three-dimensional space. As you will see, both topics might look a little bit complicated at the start, but in fact, they are fairly easy. I hope that by the end of the first 45 minutes, you will agree with me. So let's warm up by solving a couple of exercises. And these exercises have to do with orthogonal vectors and lines, which are two of the things that we were working on last Tuesday. Okay, here are two vectors. They are two-dimensional vectors. One of them is fully specified. That's u. Its coordinates are u and minus 1. The other one is a vector with unspecified coordinates x, y. So what I want you to do for me is to tell me how I can find out for what values of x and y the vectors u and v are going to be orthogonal. Now, in case this word orthogonal does not ring any bell, well, it means basically they are going to be perpendicular to one another. So the angle between the two vectors is going to be a right angle, 90 degrees. That's what orthogonal means. Okay, how can we figure out for what values of x and y these two vectors are going to be orthogonal? And of course, the people at home are welcome to work with us. In fact, that you stop the recording or the video stream and work on this problem before restarting the video stream. So orthogonality of vectors has got to do with one of the operations over vectors that we introduced last time around. And what operation is that? The dot product, as one of your colleagues is saying here. Two vectors are orthogonal if and only if their dot product is equal to what? To 0. So in order to figure out for what values of x and y the two vectors u and v are orthogonal, what we need to do is to compute the dot product of u and v, which is going to be what? X minus y, as one of your colleagues here is saying. This expression, which is a number, is going to be a real number once we plug in values for x and y, is the dot product of the two vectors. Why is that? Well, because the dot product is obtained by taking the product of the entries which are positioned in the first coordinate of the two vectors, 1 and x, that's going to give us x. The product of the second components, minus 1 and y, that's going to give us minus y, and we sum them together. So x plus minus y is x minus y. And this thing has got to be equal to 0 in order for x and y to be orthogonal. Oh, sorry, for u and v to be orthogonal.
So if x minus y must be 0, then they would not be the same number?
Absolutely. Your colleague is saying, well, x should be equal to y in order for the two vectors to be orthogonal. So basically, x minus y equals to 0. This describes a line in the two-dimensional space. And what line does it describe? The line that consists of all of the points. So if this is 1, the 0.11, that's going to be the line going for, well, sort of, should go through the origin. Let me redraw this. And let's see whether I can succeed in making it go through the origin now. I can't actually, so I'll make it thicker. So it goes through the origin. Okay, so that's the line which is described by x minus y equals 0. It says x and y must be the same. And now if you look at the other vector that we had before, that's going to be the vector 1 minus 1. So if this is 1, that's going to be minus 1. So that's the point we are looking at. And this vector here is indeed at 90 degrees with any of the vectors along the line. So for instance, if we take this point here, this point is going to correspond to this vector here, the blue one, and that spans a 90-degree angle with the vector u that we had before. Okay, so this is one of the uses of dot product that we saw last time. You can use dot product to figure out whether two vectors are perpendicular. They are perpendicular if and only if their dot product is 0. Any doubt about this? We just used the definition, essentially, of what it means for two vectors to be orthogonal, and the definition of the dot product that tells us how we can actually compute the dot product of two vectors. So let me ask you another question related to the dot product, since we are keen dot products, productors, whatever. Okay, so suppose that I have a vector u. I have my vector u, which consists of the number a1 to an. And suppose now that I want to compute the average value of the components of this vector using a dot product with another vector. Which vector should I use to compute the average value by means of u by means of a dot product operation with another vector? Okay, your colleague, one of your colleagues here is saying, well, I can use a vector that only consists of ones. Okay, so let's see. Let's see. What happens if I take the dot product of u and this v that only consists of ones? What is it that I get? I get a number, but what is this number? It's the sum of all of the elements of u, as your colleague here is saying. Okay, so, but that's not the average. Okay, we're getting close, actually, because what would be the average of this thing? You have to divide by n. So instead of 1 here in as the coordinates of v, what coordinates should I get? Because actually dividing by n corresponds to taking a1 divided by n plus an divided by n. So in other words, I multiply each one of the ai's by 1 over n. So instead of 1 in v as the constant coordinates, here I should take 1 over n. So actually using dot product, you can compute averages of your data stored as a vector. By multiplying with an appropriate a vector, where appropriate means it must, of course, have the same dimension, the same size as the vector of whose coordinate you want to compute the average, and then all of its entries will be 1 over n, where n is the number of entries in the vector you want to compute the average of the components of. Okay, so there is quite a bit that this simple operation dot product can do for us, amongst all of the other actually more interesting applications that we saw in our previous course session. Okay, so are you warmed up with dot products? Yes, I think you are, and the people at home are just on fire now. I'm pretty sure about that. I say at home because I assume people are at home. They might just as well be in Teo Cafe or wherever it is. In fact, Teo Cafe probably here in the university. Okay, so let's try to refresh our memory of lines now. So let's look at lines in three-dimensional space. I'm going to give you 2 points, A, whose coordinates are 1, 0, 1, and a point B, whose coordinate is a 0, 0, 1. And I ask you, what is the equation of the line that goes through these 2 points? Okay, well, these are 2 points. Between any 2 points, there is exactly one line. So what is the equation of the line that goes through these 2 points? Now, those of you who watched the previous lecture or who read the material or who did both will know that there is one important vector that determines a line, that determines in which direction the line goes. And what's the name of this vector? It's the direction vector, exactly. So I was not pulling your leg when I was saying in which direction it goes. It was a subliminal message, not so subliminal after all. Okay, so what we need in order to write the equation of the line that goes through these 2 points is to find a direction vector for this line. Well, actually, this line has to go from A to B because it has to cross these 2 points. So what would be a natural choice for a direction vector, It has to go from A to B, so, well, the vector that goes from A to B is a good choice for the direction vector. So let's take our direction vector D to be the vector that goes from A to B. And now, what is this vector? Well, it's B minus A. Yes, absolutely. So it's 0, 0, 1 minus 1, 0, 1. Because these are the 2 vectors that correspond to the 2 points. The vector that goes from A to B is B minus A, which is the vector minus 1, 0, 0. Okay, but now we are in business. Why is that? Because we can use the formula for the equation of the line that goes through point A, and that's direction D. What is this formula? This formula tells you that any point x, y, z on this line can be obtained by starting from A, which is 1, 0, 1, and then multiply the direction vector by some real number. Where this thing here is the direction vector D. that we just found. Okay, so any doubt about this? In other words, as Archimedes said many times, well, a few years ago, more than 2,000 years ago, give me a lever, I will lift the world, long enough lever, I will lift the world. Well, your version of this for this type of exercise is give me a direction vector, give me a point, I will give you the line. Yes?
Can you explain this line?
Okay, the question is, can you explain the last line? Well, this is the equation for a line that goes through a point. In this case, the point that I chose is the point A. And that has the direction vector D. It's a formula. It's a formula that you can just plug in. Once you have an A, you have a point, and you have a direction vector. This is always going to give you the line that goes through that point. Last time we argued why that formula actually describes a line that goes through that point, but it's easy. It certainly goes through that point, because if you take t to be 0, then you get the point A. So x, y, z can actually be the point A, and any other point that lies on the line will have to be reachable from the point A by traveling along the direction given you by the vector D. And how long you need to travel is given by the value of t, essentially. Question? I could have also chosen B, absolutely. The question is, you could have chosen, well, it was actually a statement, you could have chosen B, absolutely. And in fact, I could have also chosen to take the vector from B to A. The only thing that would have changed is that the formula would look differently, but they would actually be the same, modulo some change of some change of the value of the parameter t. You will get exactly the same set of points. So in other words, you cannot get this wrong. If you know how to write the equation of a line, you can only get it right, but in many different ways. Okay, so look at the fat arrow, which should be red, even though it doesn't look that red on the screen here. But I'm color blind, so you shouldn't trust me. This is really the thing you need to remember. And in fact, you don't even need to remember it because there's very little to remember. You can actually write it down on your cheat sheet at the exam. You will be allowed to take a 1A4 piece of paper with all of the formulae that you don't need to remember, that you may find useful. Okay? So now you're really warmed up. Since I don't want you to burn out before we cover the new material, let's look at the new material. So we'll start by looking at projections. That's kind of a natural operation. I mean, you have a vector, you want to project it, for instance, on the x-axis or on the y-axis, or do all kinds of stuff. In general, direction vectors will play a role also in the computation of projections. Because you may want to project a vector in the direction of a line, for instance, defined whose direction vector is d. So let's phrase this as a computational problem. You're given as input a non-zero vector d, which you can think of as the direction vector for a line. And you're given an arbitrary vector u. It is often useful to be able to somehow split express the vector u as a sum of two vectors, u1 and u2, where u1 is a vector that is parallel to the direction vector. So you can think of it as the part of u, the contribution of u along the direction of the vector d, and a second part which is orthogonal, that is to say, it is perpendicular to the direction vector. Question is, how can we find these two vectors u1 and u2 with these two properties such that U is actually the sum of these two things. Oh, let's try to draw a picture. And I say try because you know that sometimes I'm not very good at it. Okay, so let's see. Suppose somebody gives you a, say, a line whose direction is given by a direction vector D. And sort of, suppose you have a vector, that's my vector U. So what I want to do now is to sort of show you how you can write U as a sum of two vectors with the following properties. U1 is parallel to D. To the direction vector. And U2 is orthogonal to the direction vector. So let's try to do that. Well, one thing that we can do is to somehow project the vector U on the direction vector, on the line determined by the direction vector. So what does this mean? That I take this point here and I go down 90 degrees. So you basically start from the tail of the vector U, and you take your laser beam and you make it go down towards the line with direction vector D. When you hit the line, that's going to be the tip of the vector U1. Well, but remember, we want to express U as a sum of the vectors U1 plus some other vector U2. So what is a good choice for U2? Rock away, I will follow. In case you follow the band.
The laser beam.
It's absolutely the laser beam, as your colleague is saying. So let's make it red. So this is actually our vector U2. And you know, the sum of these two vectors is going to be exactly U. Why? Because if we start here, you do U1 plus U2, you actually get U. You go to the same point where U goes. So in fact, U2 is nothing but U minus U1. This sort of looks intuitive. So the only thing we are left to do is to compute this vector U1, because once we have U1, we had U already. If we have U1, we can also compute U2. So what is U1? So let's try to see. Well, first of all, U1 is parallel to the direction vector D. But what is it that we saw last time? That one vector is parallel to another one if it's a multiple of that vector. So actually what we know is that U1 can be expressed as T times the direction vector D, because it is parallel to D. For some real number T. Okay, but now this tells us something about U2. Therefore, U2 is actually equal to U. Oh, I'm putting the U minus T times D. But now look at what I said here. One of our items on our wish list was, dear Father Christmas, give me a vector U2 which is orthogonal to D. Well, when is U2, namely this thing, this expression that I just wrote, orthogonal to D? When their dot product is 0. We just saw that. So let's compute the dot product. U minus T times the direction vector D dot product with D, this thing should be 0. But hey, what is this thing? Now, remember last time we saw some properties of the dot product. You can actually distribute here. So this is the same as the dot product between U and D minus T times the dot product of D with itself. But the dot product to D with itself is related to what? To the length of D. It is actually the square of the length of the vector D. So this is equal to the dot product between U and D minus T times the length of the vector D squared. And now we know what T is actually. So let me rewrite this thing. T must actually be equal to, since this thing here is 0, T must be equal to the dot product of U and D divided by the length of D squared. Which tells us what U1 and U2 are. In particular, U1, which is the projection of the vector U along the direction D, is T times D. So it's this thing here times D. This is D, the direction vector.
I was wondering though, when you had the picture up there,
Yes.
there was another way to compute this. If you scroll up, you would find a vector that's perpendicular to D, and then find the point that U points at.
Okay, yeah. So your colleague in the room is pointing out that there is another way of calculating this. Sort of first you find a vector that is perpendicular, and this will tell you at what point you actually hit the line. And then if you knew what is the start point, the tail of this of this vector, then the vector going from it to this point would be U1. I just find it simpler to do it this way. You're absolutely right. There are more than one way of doing this. Both ways will lead you to the same formula, which is the one that we just have found out. The reason why I also give you this is not, well, I feel it's slightly simpler, and it's the thing that you will see in the book, so I don't want to confuse anyone. But yeah, there is more than one way in general of doing the same thing. Absolutely. Good point. Okay, so this is how we go about doing this. In fact, you don't really need to remember all of the steps that we're going through, even though, I mean, it's sort of satisfying to figure out that this formula, which looks on the face of it pretty strange, in fact, is actually not strange at all, because you would be able to reconstruct it by following a few easy steps, given time and patience. I will not ask you to reconstruct the argument for the formula, but it could be useful to remember the formula, at least, or at least to write it down on your A4 sheet of paper for the exam. So what is, the question is, what is this? This one. Oh, this is a D. Since my first D perhaps was not sufficiently clear, I made it even less clear. So let me, whoops. Yeah, there you are. There were two Ds, one on top of the other, which make it look like something else. But there you are. Now you have to do, you have a choice between two versions of the D. Okay? And you will be doing exercises related to projections and all that stuff. So now we know how to compute projections. There's one thing that I promised you that we will be looking at, and that's planes, equations for planes in 3 dimensions. So let's do it on our virtual sheet of paper. Now, already I have trouble drawing in 2 dimensions. Planes are 3-dimensional things, so you will have to abstract away from some of my bad drawing, but the important thing is the idea. So suppose that I have a plane like this. And I know that I have a point here with coordinates x0, y0, z0, which lies on the plane. Well, you can think of a plane as an infinite sheet of A4 paper, which wouldn't make it an A4 paper, but anyway, it's an infinite sheet of paper. And all the points of this plane. So you want to give an equation that completely characterizes all of the points in this plane, just like an equation for the line characterizes all of the points on that line. Now, it turns out that orthogonality plays a role also in coming up with a very simple description of all of the points that lie on this plane. Why? Suppose that I tell you that I have a vector which people refer to as a normal vector that is perpendicular to the plane. It's orthogonal to the plane. Okay? And let's say that this vector has coordinates A, B, C, as we are in 3 dimensions. I give you this vector with coordinates A, B, C. They are constants. Now, what should be true for a point with coordinates x, y, z in order for this point to lie on the plane where the point x0, y0, z0 lies, and which has this vector sticking out of it at 90 degrees. Okay, so let's see. If I take the vector that goes from P0 to P, what is the angle that this vector will form with the normal going up? 90 degrees. So this thing will be a right angle. But then look at the vector that goes from P0 to P. And look at the vector n. These two vectors are what? They form 90 degrees when so they are orthogonal, which means that their dot product must be 0. And this is true for every point x, y, z which lies on the plane. Because all of the vectors from any point, in fact, I mean, I could have chosen that point anywhere, any vector will have to span a 90-degree angle with the normal, because the normal is always sticking up. It's like a piece of the heat vector that goes up from each point in the plane. But hey, now we have actually the equation for the plane. Why? Because we can actually compute this vector. What is it? It's P minus P0. So it's x minus x0, y minus y0, z minus z0. Time, sort of dot product with ABC, and that should be 0, where this is, well, that should be 0. So what does this mean? That the equation is a times x minus x0 plus b times y minus y0 plus c times z minus z0 equals 0. That's nothing but the expression for this dot product of the two vectors. And that's the equation for the plane. Of course, of the plane with normal vector n and going through P0, x0, y0, z0. So what is the motto, which is the counterpart of Archimedes' Archimedes' lever motto for planes is, give me a normal vector, give me a point, I'll give you the equation of the plane on which that point lies, and that has that normal vector sticking out of it everywhere. And that's the equation. It's not even complicated, is it? So suppose now, before the break, I ask you, you know, I haven't had lunch so far, so I like to eat planes for lunch. Well, I cannot digest them very well, but sometimes I try. So suppose I ask you, I got this normal plane for my last birthday. So this normal vector for my last birthday. And I like my point P0 to be the point 0, 2, 4. What is the equation for the plane that goes through, on which the point P0 lies, and there's normal vector 1, 0, 1? This is not a trick question. You got your visual memory up there on the smart notebook. Okay, so what all we need to do is to plug in the coordinates for n and the coordinates for P0 in the formula that you have here. So A is 1. B is 0, and C is 1. And this is our x0, this is our y0, this is our Z0. So what does the formula say? Okay, x minus 0, which is x, plus b times, now b is 0, so that thing disappears, plus c times, c is 1, z minus z0, z0 is actually 4, so z minus 4 equals 0. That's the equation of the plane. Any point x, y, z whose coordinates solve this equation is going to be on the plane. What did I do here? Yes. Note the point 0, 2, 4 is on the plane, because if x is equal to 0 and z is equal to 4, then 4 minus 4 is equal to 0. Cool. Yes, question. Okay, the question is, I don't understand why this z minus 4, which we have here. Yeah. Well, look at this part here of the formula. This says c times z minus z0. Now, c is 1. So you have 1 times what? Z minus z0. But what is z0? Z0 is 4. So 1 times z minus 4 is z minus 4. The other question is, why don't you use b? Because b is 0. Oh, so you have 0 times something, that something disappears. Now I'm waiting for the third question, which is why x? Since we are, okay, yeah, you can work it out during the break. Any questions about what we did? Actually, we covered 2 formulae, and you have 2 possibilities. Either you remember them by heart, well, actually 3 possibilities. Either you remember them by heart, which is always dangerous, or you write them down on a piece of paper that you can bring to the exam in case you need them, which is sort of safe. The third possibility is the best of them all. You write it down on the piece of paper. You don't need to remember them, but you know why these formulas are actually the way they are, which is not mind-boggling, which sort of combines a visual memory with true understanding, which is what you are for anyway. You're all for true understanding. Deep learning. It's not just machines today that do deep learning or deep inference. It's also humans, or at least that's what we think. Okay, 10 minutes break, and after the break, we are going to start a journey having to do with probability theory, which is a journey you already started in discrete math 1. So this is probability, the return of probability. Okay, break now.